Hi there everybody, welcome to another MCAT ACE video, and in this particular lesson we are going to be covering periodic trends. So this is when we look at the periodic table, the various trends that we come across or the assumptions that we can make as we go across the various families and periods in the periodic table. So you can see from the outline here what we would like to cover. The very first thing, we are going to lay out a brief reminder of valence electron structure, which is the outermost set of electrons that we find in a particular column for the periodic table. We're then really, the first part of this video is going to discuss effective nuclear charge, and sometimes you may see this abbreviated as ZEFF or Z effective, charge effective. And what this really is it's a look at the proton to electron ratio, and the effective nuclear charge is going to be able to explain most of the other trends that we come across. So it's very important that you understand how effective nuclear charge works, and then subsequently you can get a grasp on atomic radius, ionization energy, electronegativity, and electron affinity, which are the major trends that we come across when we're dealing with the periodic table. So with effective nuclear charge, we'll take a look at the general trend. We're going to talk about how protons will influence the effective nuclear charge and basically what effective nuclear charge actually is, how it works. We're going to talk about what happens as we continue to pile on electrons, and specifically what happens if we open up a new shell and we place additional electrons into that shell. So in other words, what happens if I go from a 2s to a 3s? How is that going to change or manipulate the effective nuclear charge? And then the rest of these, the subsequent list here, is going to be based off of understanding effective nuclear charge. So you have atomic radius trends. This is also going to include ionic radius. So what happens if we start tossing out electrons or gaining electrons? And then we'll talk about isoelectronic sets. And isoelectronic is just a fancy word for the meaning of same electronic charge. So in other words, anything in an isoelectronic set should have the same number of electrons. Now, not necessarily the same number of protons, so that's going to be important when we come to that. Okay, then we'll talk about ionization energy and ionization energy trends. Ionization energy is the energy required to remove an electron from an atom. So we can do that. We could also do that more than once. So for instance, if I have something like magnesium that would have a 2+ charge, I have to take the first electron from magnesium, that would make it 1+, and then I would need to take a second electron from magnesium in order to make it 2+. So we're going to talk about what happens as we continuously attempt to pull more electrons away from a given compound. And then there are two major exceptions to the ionization energy trend. We'll take a look at those and briefly explain why they exist. And then we will take a look at electronegativity trends, which we have discussed in some other videos. Bond classification and polarity. So electronegativity talks about how well an element is going to take a hold of or share electrons when it's involved in a bonding relationship, and this can classify the bond as nonpolar, covalently polar, or all the way up to close to ionic, depending on the difference in electronegativity values between the bonding partners. And then finally, to wrap up, we'll look at electron affinity. And electron affinity is really the desire to gain an electron. So a lot of times students will cross electronegativity and electron affinity, which is understandable because they're very similar. But electron affinity is when an element is looking for an electron. It's actually the amount of energy that's going to be released upon picking an electron up. And so the more energy released when an element picks up an electron, the more desperately it needed or wanted that electron. Okay? And electronegativity is when you're already involved in a bond. So let's say fluorine's looking for an electron. In that case, we're talking about electron affinity. But let's say that fluorine has found a hydrogen with one electron to share. And in that case, when we're looking at the hydrogen-fluorine bond, we're talking about fluorine's electronegativity, its pull, now that it's already involved in the bond and the sharing of the electrons with hydrogen. So that's the difference between those two. Electronegativity, you already have bonds set up. Electron affinity, you have the element looking for an electron. It's not involved in a bond quite yet. All right, so hopefully that helps to clarify the difference between those two. So let's go ahead and bring up our periodic table. Okay, so here's our periodic table. And as we said, we wanted to basically look at valence electrons. That's the first thing that we're going to just briefly go over here. So with valence electrons, it's important to remember that when I come to this row here, I have one valence electron. So that's hydrogen, lithium, sodium. Now, please keep in mind, valence, again, means outer shell, outermost shell. So when I'm talking about valence electrons, okay, I'm talking about the electrons found in the outermost shell. It's not the total number of electrons. So while hydrogen does have one single electron, lithium would have 3 electrons. It would have 2 in the 1s shell, and then it would have 1 in the 2s shell. So when you're looking at these, we're talking about just the electrons in the outermost shell, the valence shell. And that's what we really tend to base most of these trends on. We're looking at the valence electron properties. All right. So going along, we've got 2 here, and we're really only going to look at group A. So the transition metals, which are group B, they do follow the same trend, but they tend to be somewhat excluded when we look at periodic trends. So you've got 3 here, and then carbons group is 4, 5, 6, 7, and 8. Now, remember that this final row over here with 8 is the noble gases. The noble gases have a complete outer valence shell. Now, most of the time that means that that valence shell will have 8 electrons, but that's not always the case. Certainly helium would only have 2 when we're talking about filling up the 1s shell, but it's the fact that you have a complete set of paired electrons in that outermost shell that's lending to the stability. So all the other elements, when they're forming ions or bonds, they're attempting to mimic the noble gases in their configuration because of the very, very large level of stability that these noble gases exhibit. And we're going to see some of that as we go through this in the various trends. So we're going to see, for instance, that they have very high ionization energy, the noble gases. And that's because if a noble gas has a full set and it's very stable, you're going to have to put in astronomical amounts of energy in order to remove an electron and ionize any of the noble gases. They want to stay exactly how they are. Okay? So again, keep in mind this is the general set of valence electrons. We go from left to right, 1, 2, jump over the transition metals. You have 3 for the boron, and then you continue onward like that up through the noble gases. So those are the valence electron numbers. Now the next thing we wanted to discuss was effective nuclear charge. And I'm going to leave those numbers up there while we're talking right now, at least while we're talking about effective nuclear charge, because we may want to go back and remind ourselves how many valence electrons we're dealing with. All right. So I'm going to scroll down here for a minute, and I want to explain what effective nuclear charge is. So again, we many times will represent this as Z effective. Okay? And effective nuclear charge is basically saying here's the nucleus, and what we find in the nucleus are protons and neutrons. Now, of particular interest here are the protons because they have the positive charge. Remember that neutrons don't have any charge at all. And so when we're dealing with our atom, let's just draw an S shell around here. If we have an electron that's basically orbiting or occupies space around the nucleus with its positive charge is going to draw in the negatively charged electron. And so this attraction, or this ability to bring in the electrons closer to the nucleus, is effective nuclear charge. That's what Z effective is. So if I take a look, I might have an atom that has a relatively low number of protons, and so it does a fairly poor job at pulling in these electrons. Okay? And then I might have an atom that's got a lot of proton pulling ability. Okay? And so it's going to have a much easier time pulling in these electrons and making them tighter. Okay? So what you can imagine is Imagine that you yourself are the nucleus, and you have these electrons that are orbiting around you. And the more protons you have, the more pulling power you have. So it's almost like tug of war. And as you continue to add protons to your team, the center, you're able to pull the valence electrons closer and closer and closer to the center. You have more pulling strength. That is effective nuclear charge. So the more protons you have, the better off your effective nuclear charge is going to be. You have more pulling power towards the center. Now there's a couple things that are important here. All right? So we understand the pull of the nucleus, but what we also want to understand is there's not always a single electron that's hanging out in a shell. So if I'm going to take a look at an example where I have multiple electrons, then I'm going to want to consider how those electrons affect one another. All right? So let's say that I've got a nucleus here. It's got some protons. And then it's got multiple electrons that are hanging out here. Well, these electrons have the same charge as one another. So a negative is going to repel or push away another negative. And this phenomenon where electrons sort of block or push one another away is known as shielding. So the shielding of the electrons, they basically push one another away and they will block subsequent electrons, because remember we have more than one shell. All right, we have another shell out here. You're going to get electrons that are even further away. And these inner electrons are going to shield the outer electrons from some of the effects of these protons in the center. So imagine it like you're layering, right? You've got your first layer, they're going to feel the effective nuclear charge the most, and then the second layer a little bit less, the third layer a little bit less, and so on and so forth. So as I rack up these shells, meaning as I go down the periodic table and I increase the number of shells, in this case, I'm going to, each time I go out one more rank, I'm going to weaken that effective nuclear charge. Now, that's only partly the case in terms of the shielding, because it turns out that as I go down on the periodic table, that I continuously add protons. And as I'm continuing to add protons, as I count up in atomic number, the extra protons will outweigh the shielding. So shielding does have some effect on the effective nuclear charge. However, it's going to have only a mild effect in comparison to the protons. So what this creates, for instance, is let's say that I go from hydrogen, so here's the effective nuclear charge, right? And I say here's hydrogen's effective nuclear charge, and then here's, let's label that H, and then here's helium's effective nuclear charge, right? It's going up. And then what happens is I go to lithium, so take a look here, right? Here's hydrogen. So here's hydrogen's effective nuclear charge, right? And then here's helium. So as I'm adding protons, I'm pulling in the electrons, but then I open up a new shell when I go to lithium, right? So now I'm in the 2s instead of the 1s. So hopefully everybody sees what I'm talking about there. So in that case, when I turn around and I open up lithium, I go down a little bit. So here's lithium. Now notice that lithium still has a higher effective nuclear charge than hydrogen, which was over here, okay? And then I start to climb back up. So after lithium, I would have beryllium because I'm adding. And after beryllium, I would have boron because I'm adding. And then as I continue to go on, I would have carbon because I'm adding. And then nitrogen. And when I say I'm adding, I'm talking about the fact that I'm adding protons. And then fluorine has an even higher effective nuclear charge. And then neon's going to have a great effective nuclear charge. And then we're going to take a dip. Okay, so notice how it's working here. You go up and then down slightly as you start a new shell. However, the lithium here is higher than the hydrogen was. And then I climb up and up and up and up as I'm adding protons. And then I take a dip when I go to sodium. And it turns out that these dips, they get larger and larger as you continue to add more shells. So when you're working with this, you need to keep that in mind because you're getting further and further from the nucleus. So you're dealing with more electrons and you're going to see these effects that are occurring. All right, so that hopefully explains effective nuclear charge. The general trend for effective nuclear charge is that as I go across the periodic table, effective nuclear charge is going to increase. So I'm going to have Z effective increase as I go across the periodic table. And then as I go down the periodic table, I am also going to see that Z effective will increase again. Okay? So Z effective is going to increase this way. So we're talking about this within a specific row or column. So what I can say here is that when I look at lithium compared to beryllium, compared to boron, compared to carbon, so on and so forth, if I go across this entire row here, right, it's saying that lithium will have the smallest effective nuclear charge. All right, so let me show you what I'm referring to when we're talking about lithium here. Okay, so imagine if we wanted to look at lithium and then beryllium. So if I take lithium, lithium would have 3 protons, and in its valence shell, now it would have 2 electrons in its inner shell, but its valence shell, it would just have 1 electron. Okay? And then, that's for lithium. Then if I were to take a look at beryllium, beryllium's going to have 4 protons in its nucleus, and then when we get to its shell, it's going to have 2 electrons. So what's happening here is that the extra proton gives more pulling ability. So there's a greater effective nuclear charge. It has a greater pull on the electrons that are surrounding. And you're going to find the same thing as you go on. So let's say that I go to boron, which would have 5, and then boron's shell, its valence shell, would have 3 electrons. And that would mean that boron, let's put these here, beryllium and boron, boron's going to have an even greater effective nuclear charge or pull because we're racking up those protons as we are continuing to move along. Now, what happens in terms of when I'm going down? So that's if I go across, Z effective. I look at lithium, beryllium, and I continue as I go on. As I'm going down, I would open up a new shell. So if I consider sodium, right, sodium is going to have 11, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's getting crowded in there. 11 protons for the nucleus, and its valence would only have 1 electron. Now, you would expect that this is going to be much higher than lithium, but what you have to consider is that lithium, in this case, has 2 electrons in its inner shell and only 1 in its valence, whereas sodium has a total of 10 electrons. Okay? And then it has its 11th electron. That 1 electron is in its valence. So when you're looking at these, there is going to be more shielding going on with 10 electrons versus 2 electrons. And so that's why when you have sodium, sodium will be higher than lithium because of all the extra pull from the protons. However, it turns out that once we get over here with neon, and we look at neon's effective nuclear charge, and then we jump to sodium, which would be next, sodium is actually going to go lower than neon did. However, it won't be lower than lithium, and it won't be the same as lithium, okay, because it has extra proton pull. But it's the fact that there is more of this shielding going on that it takes a dip from where neon was. So that is effective nuclear charge, and we are going to take a look at how this can explain atomic radius trends and all these others that we've listed up here. So that's what we're going to take a look at next. Let's prepare to look at atomic radius trends and how those would work. All right, so now that we've cleared the board here, let's take a look at the atomic radius trends. So for the atomic radius, the general trend that you're going to see is that the radius, as we go from left to right, it's going to decrease going this way. We'll talk about why in a second. You should be thinking about why this is the case as we're going through this, because we just talked about effective nuclear charge, so try to scaffold that in and think about that. So we're going to decrease in size as we're moving this way, and then as we're going down this way, we are going to increase in size as far as the atoms go. Alright, so let's knock the easy one out first. Why do we increase in size as we go down the periodic table? So in other words, why is hydrogen smaller than lithium, and lithium smaller than sodium, and sodium smaller than potassium, and so on and so forth? Well, the answer for that is that we are adding additional shells. So as we add additional shells, 1s, 2s, 3s, 4s, as we're expanding those quantum levels, what's going to happen is we're also going to increase the atomic radius. So the atomic radius, by definition, is the distance from the nucleus to the outermost valence electron. Well, if the valence electrons are occupying shells further and further from the nucleus, it would only make sense that it's going to increase as we continue to add more shells. Now, what's going on as we go across, right? As we're climbing an atomic number, so I usually like to use the second row as an example, lithium, beryllium, boron. You're going to see me come back to that a lot. So as we're going across, we're saying that we're decreasing in size. So we're saying here that lithium is the largest in this group, and neon is the smallest in this group. So why is that the case? Well, if you were thinking about it, the reason for this is that as we go across, we're increasing Z effective. So think about what's happening. Lithium has the lowest Z effective, or the lowest effective nuclear charge. So lithium struggles to pull in its valence electron in comparison to beryllium. Beryllium has a better hold, and it can pull its electron set in a little bit tighter. Boron can pull it in even a little bit tighter. Carbon can pull it in even a little bit tighter. So on and so forth. So as the effective nuclear charge increases, it's pulling the electrons in closer, closer, closer to the nucleus. And that means that we're getting smaller and smaller as we're going across. Again, until we add a new shell. So we get to neon. Neon's going to be itsy bitsy compared to lithium. But then when sodium comes, we're talking about adding an entirely new shell onto this atom. And so at that point, we're talking about an increase, and we're going to jump up in atomic radius when we're working with that. So that is general atomic radius, right? Now, what we want to consider next is what's going to happen if we start talking about ions. All right, so let's clear the board here. If we are talking about ionic, meaning we've now removed electrons or added electrons to the normal elemental form, what are we going to see occurring? Well, let's start with cations. So if I take a look at a cation, and we'll go ahead and we will continue to use things from the second row. So let's use lithium, right? So normal lithium is going to have 3 protons in the middle, and then in its valence shell it's going to have 1 electron. Now remember, there's a total of 3 electrons there, but the valence shell only would have 1 electron. Okay, so there we go. That's going to be normal lithium. So what about lithium, the cation? So lithium plus, because we know that metals like lithium give up electrons. Well, in a case like this, you're then going to have 3 protons, but you're not going to have any valence electrons. This is going to be empty. And so you're only responsible for pulling in the inner electrons, those 2 inner electrons. And so what happens is I'm changing the ratio here. So right here, and a lot of times students see this easier with ratios, right here I have 3 protons to 3 electrons total. Whereas right here, I've got 3 protons to 2 electrons total. So which one's going to have more pulling power? Well, if I have an additional proton in comparison to my electrons, because I've lost an electron, this is going to be able to have a tighter pull, so this will pull better. And if this can pull better, it's going to be smaller. So that means that the cations will be smaller in size relative to their counterparts, their neutral element. All right, so keeping that in mind, what do you think is going to happen with anions? All right, so take a minute to think about it while I delete the board here. So if I have an anion, what would form a good anion? Let's talk about fluorine, right? So fluorine is going to have a total of 9 protons in its nucleus, and in its valence, it's going to have 7 electrons. So 1, 2, 3, 4, 5, 6, 7. All right, so a total of 7 electrons. Let's keep our numbers here for ratios in a minute. So fluorine has a tendency to form F-, which is going to be an anion. So now we're talking about anions instead of cations. And when we have an anion, right, what we're going to work with here is the gaining of an electron instead of the removal like we had with the metal. So we still keep 9 protons, but now we're looking at gaining an electron. So now we have a total of 8. So counting, there's 4, there's 5, 6, 7, 8 electrons for F-. Now if I come and I take a look at the ratios here, right? Here I have a ratio of 9 protons to 7 valence electrons, okay? And here, now this would be a total of 9 electrons. Let's do that, okay? Let's actually keep it because that's what we were doing before. We were counting it based on the total electrons there. So this has a total of 9 electrons, 2 in the inner shell, 7 in the outer. And this one, okay, hopefully this won't confuse people then if we're keeping it the same, has 8 electrons in its valence shell, but again it has those 2 inner from the 1s shell. And so it has 10 electrons total. So look at the ratio here. We've gone from 9 to 9, from 9 plus to 10. So what's happening? I have an extra electron that's going to repel other electrons, and I'm not buffing up or increasing the number of protons. That's going to be problematic if I'm doing that, because when I get to this point, electrons are going to push one another further apart, and I'm not increasing the number of protons. So the same number of protons are responsible for pulling in an additional amount of electrons. That's going to be difficult, and so this is going to actually get larger in size. The protons are going to lose a little bit of their grip when I'm shoving in extra electrons without compensating and adding in another proton. So anions tend to get larger in size when we're working with them. Right? So that is an example where we're talking about ionic radius. So you have atomic radius, which is in your neutral form, and then you can have ionic radius. Remember, cations get smaller and anions get larger. That's what you're looking for there. Right? Now, we did mention at the beginning isoelectronic sets. So these are groups that all have the same number of electrons. And if we're working with those, in fact, I was sort of just alluding to one. Let's say that I have O2-, and I have F-, and I have neon, and I have sodium, and I have magnesium 2+. All right, so I take a look at all of those. If I look at all of these, they all have the same number of electrons. So looking at all these, they would all have a total of 10 electrons associated with them. Okay, so neon being the neutral form, and then I have some of the anions over here, and then I have some of the cations over here. Well, we know that the general trend here is that anions are going to be larger in size and cations are going to be smaller in size than their counterparts. And so what we're looking at here in terms of size, even though all of these have 10 electrons, the size is going to decrease as I'm going this way from ionic form. So that is to say, my anions, O2 minus would be the largest, then F minus, then neon, then sodium, then magnesium. I'm going to decrease in size as I'm moving along this way. Okay, and again, that's because what I'm increasing over here, okay, this is decreasing, let's make this clear, decreasing size, but what's increasing, okay, is the number of protons. So that's to say that when I go from oxygen to fluorine, I add a proton. When I go from fluorine to neon, I add a proton. When I go from neon to sodium, I add a proton. So what's happening every time I add a proton? Well, it has greater pulling ability. It can pull these electrons in to a greater degree. Now, still dealing with the same number of electrons total, however, the number of protons are not remaining consistent. Okay, so that's why we can see variation even though the number of electrons are all the same. So again, this is referred to as an isoelectronic set. Isoelectronic set of ions. So that covers the atomic radius trends. So again, let's just go up and recap. I've got an increase in the atomic radius trends as I go down, and I've got a decrease in the atomic trend as I go across. So that's for the radius size. So the next thing we're going to take a look at is ionization energy. So let's go ahead and clear this board, and then we'll take a look at ionization energy. Okay, so ionization energy, again, just to refresh, is the energy required to remove an electron from the valence shell of an atom. So, if you think about the periodic table, metals will form cations, meaning metals are more likely to lose electrons, whereas the nonmetals are going to be more likely to gain electrons. So I would expect that the ionization energy is going to be easiest for the metals and most difficult for the nonmetals. It's going to have the highest cost for the nonmetals in terms of the energy I have to put in order to create an ion or remove an electron is what I'm really talking about here. So when we look at this, all right, think about the effective nuclear charge again. The electrons are being held on tighter and tighter and tighter as I move across the periodic table. So I have a greater effective nuclear charge as I move this way, meaning the electrons are held on to a little bit tighter every time I go across by the nucleus. Well, if that's the case, and these electrons over here on the right side of the table are held on to with a tighter grip than those on the left, I would expect that my ionization energy is going to increase as I'm going along here because of the effective nuclear charge. So you can see why we looked at effective nuclear charge first, because it helps to explain a lot of the trends that we're seeing here when we get into this. Right? It also turns out that as I go up the periodic table, the ionization energy will also increase this way. So I get an increase in ionization energy as I move up. And that's because when I look at the atomic size, when shells get further and further and further out from the nucleus, they're losing some of that pull, and so it's easier to come in and remove an electron from that valence shell. So, for instance, if we look at the halogens here for a second, fluorine is smaller than chlorine, is smaller than bromine, is smaller than iodine. So iodine's the largest out of the bunch. If I look at the valence electrons in iodine, they are going to be very far removed from the nucleus. They're going to be way out there. So it's going to be easier to pick one of those off and put in the ionization energy than it is for fluorine. So that's why I see an increase in ionization energy when I'd like to remove an electron from fluorine in comparison to iodine. It has to do with the size, the distance from the nucleus. Now when I'm coming across here, so let's say that I'm looking at boron and carbon and nitrogen, right? As I'm coming across, this is saying that if I look at boron, it's going to be more difficult to remove from carbon than boron, and it'll be more difficult to remove from nitrogen than it will be from carbon. All right, now the reason for this is the effective nuclear charge, because carbon holds on to the electrons a little bit tighter than boron does, and nitrogen holds on to the electrons a little bit tighter than carbon does. So it requires more energy to come in and to remove one of those than it would for the previous one in the set. So that is ionization energy. Now, you can remove more than one electron when you're doing this. So for instance, I could turn around and I could say that I would like to remove an electron from magnesium, right? I think this is the example we were giving at the beginning. If I have magnesium in its valence shell is going to have 2 electrons. And so if I look at these 2 electrons, I'm putting negative charges there for each of them, okay? To remove one electron, I call this the first ionization energy, which we'll abbreviate as IE. So it could have been either of these 2 that I picked, but in order to remove this, the first ionization energy level must be reached. And I have to put in a certain amount of energy to do that. But then, after that's been removed, and I'm dealing with magnesium plus, I'd like it to become magnesium 2 plus, so I need to remove a second electron. So this is known as the second ionization energy. And you can continue to build up. You could have third, fourth, fifth ionization energies when you're talking about this sort of stuff. Okay? So every subsequent ionization energy is going to be more costly than the previous one. So that is to say that it is easier to remove the first electron from magnesium than it is the second electron, right? And think about what happens by the time I hit a second electron. Here's magnesium. I lose 1 electron, I'm in the configuration of sodium. I lose a second electron, I'm in the configuration of neon. Well, now I've hit the configuration of a noble gas. And that is going to be incredibly difficult to start taking away additional electrons. So it turns out that ionization energy is going to be highest when you hit this point, the noble gases. Oops. You've got the highest, sorry, I'm getting cut off there, highest ionization energy at that point. So the noble gases, again, are the stable configurations. So once you get to a noble gas configuration, you're going to see a massive jump in ionization energy in comparison to anything that came before that. Alright, so that explains the levels of ionization energy. Now what I did mention was that there are some exceptions to this, and I want to talk about both of those now. So give me a second to clear this and we'll talk about the exceptions. Alright, so for the exceptions, what we're going to be looking at, let's use a different color here. Alright, it's going to be whenever you jump from the end of an S shell to the beginning of a P shell. So this would apply for magnesium and aluminum, it would apply for beryllium and boron, it would apply for calcium and gallium, and so on and so forth. All right, so this is the first exception. And the reason for this exception is because we are jumping from an S shell to a P shell. So what happens is it turns out that the ionization energy for the P shell is going to be slightly lower than that of the S shell. Now we're talking about just the very end of the S shell. So not lithium, it would go higher from lithium to beryllium. And then when we go from beryllium to boron, we're going to find that beryllium had a slightly higher ionization energy requirement and boron had a slightly lower one. Now the reason for this is that the S shells are closer to the nucleus. These are closer to the nucleus. Okay. Whereas the p shells are going to be further from the nucleus, so they are slightly easier to take from when you make this initial jump. Okay, now the other area that we see this type of exception is when we jump from the middle of a p shell to the second half of a p shell. So phosphorus and sulfur show this behavior, nitrogen and oxygen show this behavior, and that has to do with the p shell configuration. So I'm going to come down here and I'm going to show you. Let me just get rid of this. When we end up with a p shell configuration, remember that it would look something like this, and I would have this for nitrogen, and then for oxygen the p shell is going to look like this. Because I introduce some pairing here, there is slight repulsion when those electrons come together, and so it's easier to remove this than when they were all individually filling one of the orbitals. So a lot of students then ask, well, once I go to fluorine, right, because that's nitrogen, this is oxygen, if I go to fluorine, I'm filling up another one like this. And they say, well, isn't it the case that then that would have even more repulsion? It does have a little bit more repulsion, but what you need to remember is the effective nuclear charge is increasing as we go this way, right? So if it's increasing as we move our ionization energy over that way, then that means that the fluorine has enough effective nuclear charge that it outweighs any of the minor electron repulsion. So that's the reason for that. So those are the two exceptions. You're going to see that the nitrogen, oxygen, phosphorus, sulfur, those types of splits are going to show that the ionization energy is slightly lower on this end for the oxygen, and it's going to be slightly higher for the nitrogen and the phosphorus. So just wanted to point those out because those are two exceptions to the ionization energy. So if we take a look and we come back up here, the next thing we want to talk about is the electronegativity trends, and then we're going to wrap up with electron affinity. So let's clear the board and then we'll talk about electronegativity and bond polarity. Alright, so when we talk about electronegativity, remember that this is talking about atoms that are already involved in bonds. So if we come down to the periodic table here, we're going to find that the general trend for electronegativity is going to be similar to what we just saw for the ionization energy. So electronegativity, which I'm going to abbreviate EN, is going to increase as we go across the table. Okay? Electronegativity is also going to decrease as we go down the table. The most electronegative element is fluorine. So if I take a look at fluorine, it is going to be the most electronegative element, and francium down here is going to be the least electronegative element. So that's the trend. Notice that the noble gases are excluded from this because noble gases tend not to form bonds with other elements. You certainly can in some cases. However, the general rule is that the noble gases remain by themselves, they're stable, they're not looking for bonding partners. And so fluorine is the highest on this list, and then as you go down, the general trend is that it will decrease going down this way. So there's a general movement like this in terms of the electronegativity trend, and it stops with fluorine. So if we continue to take a look at this, we can classify bonds as being polar or nonpolar, and they can even get as high as ionic, which is extremely polar when we look at this. Now, what you have to consider is the relative electronegativity values and the difference between them. So let me give you a few examples so you understand what we're talking about. Hydrogen, and this is going to vary from chart to chart, but if you look up hydrogen, it's going to have an electronegativity value of about 2.1. Okay, carbon is going to have an electronegativity value of around 2.5. And then let's say fluorine. Fluorine is going to have an electronegativity value of about 4.0. So if I take a look at these, a carbon-hydrogen bond, if I look at the difference between these, I have 2.5 minus 2.1. So the difference here is 0.4. All right, now if I have a carbon-fluorine bond, I'm now looking at a difference of 4.0, now that's for the fluorine, minus 2.5. And I'm looking at the absolute values here, because if you flip that and you do 2.5 minus 4.0, you're taking the highest one minus the lower one. So when I take a look at this, I now have a difference of 1.5. It's a much larger difference than the 0.4 that we had over here. So carbon-hydrogen bonds are usually considered to be non-polar or hydrophobic when we look at them. However, a carbon-fluorine bond would be considered polar when we're looking at it. So a lot of times you'll see the partial positive and the partial negative charges associated. In this case, carbon would be partially negative, the hydrogen would be partially positive. But the difference here is not large enough to create a real polarity difference. There's minor differences, but we would generally classify this as non-polar, and then we would classify the CF bond as polar because of that difference. So there are cutoffs when we look at this, and again, these are going to range from source to source when you're looking at them. But in general, what we're talking about here is that if there's a difference in a bond from 0, meaning the same element is bonded to itself, for instance, oxygen is bonded to another oxygen, all the way up to 0.4, it's going to be ranked as a non-polar covalent bond. So remember, covalent means a sharing of electrons. If we have 0.5 to 1.9 as the difference, then you're looking at a polar covalent bond. And keep in mind that this is a sliding scale. So in other words, if I have a difference of 0.5, it's just slightly polar covalent. It's almost nonpolar. Whereas if I have something that's 1.9, we are extremely polar covalent to the point that we've almost become ionic. And that brings us to the next point, which is that if you have a 2.0 difference or greater, then in that case you're dealing with a bond that is ionic. Ionic bonds are incredibly polar. They no longer really share electrons, so we don't call this covalent. There's a transfer of electrons going on because one compound has such a strong pull in comparison to the other one that there's really not any sharing going on anymore. And these are very typical of salts. So when you have a metal and a non-metal together, you're usually going to get large drastic differences in the electronegativity values. You come up with ionic compounds. So it is important to remember that fluorine is the most electronegative element, okay? And then we decrease as we go back down this way, or you can say that you increase as you're going up towards fluorine from the bottom corner. And that makes sense. The metals are going to be less electronegative. They are not going to hold on to electrons when they're involved in a bond very well. So just to recap that, and I know we mentioned it briefly before, when we're talking about electronegativity, electronegativity is really referring to how well an element or an atom is going to hold on to the electrons being shared in a bond. So let's say hydrofluoric acid. If I have HF, right, and I can put the lone pairs of electrons here, these are going to be shared, the ones that are represented by the bond. And when I look at hydrofluoric acid, the fluorine has a value of 4.0, the hydrogen has a value of 2.1. So if I look at this, the difference between these is 1.9, so I'm almost to an ionic bond. I'm real close, okay? And if you look at the difference here, it's saying that the fluorine has the stronger pulling power on the electrons, and the hydrogen has the weaker pulling power on the electrons. So the general flow of electron activity from this shared bond is going in the direction of the fluorine. You might call that a dipole moment or a dipole vector that's being shown in this molecule. All right, so that is electronegativity. And then the last thing that follows a very similar trend, and I mentioned it at the beginning, sometimes students confuse these, is electron affinity. So that's the last topic we want to cover in this video here. All right, so let's clear this and then we'll talk about electron affinity. All right, so we've got a fresh periodic table up. Electron affinity is going to have another similar trend to the one we've been seeing, in which electron affinity is going to increase as we go across the periodic table. Electron affinity is also going to decrease as you're going down the table. Now, I will mention electron affinity has a lot of bizarre exceptions, so we're not going to get into all of those. The general principle or trend is what you're looking for here, which is fine. So electron affinity is going to decrease as you go down, and it's going to increase as you go across. And the general premise for this, again, electron affinity is the amount of energy that's going to be released when an electron is picked up by a specific element. So it makes sense that the closer we get to the noble gases, the more likely it is that there's a high need to pick up electrons. So there's strong desire for electron pickup by the halogens, and so you're going to see very high electron affinity for the halogen group. And then you will continue to see a general trend where it decreases, certainly over in the metals. You would not expect metals to be looking to pick up electrons at all. They're looking to get rid of electrons so that they can retreat to the previous noble gas configuration. Again, various exceptions here, but the general trend should serve you well. Note that these, not halogens, these noble gases are going to be exempt, like before, from the trend, because when we have electron affinity, this is the desire to pick up an electron. Noble gases already have full, complete sets. They're not looking to pick up any additional electrons. All right, so with that being said, that covers all of the trends, so let's go ahead and try some problems. Okay, so here are some questions. The first one says, which of the following would be a polar covalent bond? So keep in mind, you're going to need to understand electronegativity in order to answer this question. Which atom would have the highest effective nuclear charge out of that bunch? And then which ion of the bunch down there would be the largest? So you have calcium 2+, sulfur 2-, chlorine -, and potassium+. So take a minute or two, pause this video, see if you can answer these, and then we will go over the answers together. So please pause the video and we will discuss them in just a minute. All right, welcome back. I am assuming at this point you've had a chance to attempt to answer these questions for yourself. So if I am to take a look at this, the correct answer for the first one is going to be that carbon-fluorine is a polar covalent bond. So if we keep in mind that electronegativity values are going to increase as we go across the chart here, from hydrogen all the way over to helium and the noble gases. Again, the noble gases are excluded, so fluorine's the highest. We have fluorine with a very high electronegativity. Then we have carbon with an intermediate, and then hydrogen would be lower. So out of all of these, if I come and I take a look, fluorine with fluorine, okay, if you remember the values, it's 4.0 and 4.0. So there's no real difference there. So we're not going to call that a polar covalent bond. And by the same token, we wouldn't call a carbon-carbon a polar covalent bond because those are both 2.5 in their values. Carbon-hydrogen, if you remember, we took a look at it was 2.5 and 2.1. So that's not a great enough difference to really classify it as polar. That leaves the carbon-fluorine bond where the difference was a little bit larger. So we had 2.5 and 4.0. So the difference was 1.5 in terms of the electronegativity difference. That's enough to classify that as a polar covalent bond. So C is the correct answer for that one. Which atom would have the highest effective nuclear charge? Well, we know that effective nuclear charge increases as we go across the periodic table. So let's take a look at these groupings here. Sodium, aluminum, sulfur, and argon. So we've got sodium, aluminum, sulfur, and argon. So if it's all in this row, effective nuclear charge is increasing as we go across here. Okay, then that means that as we get towards the end with argon, that's going to be the highest of the bunch. So the correct answer here is D. Argon is going to have the highest effective nuclear charge. And then finally, which ion would be the largest of this bunch? Well, we know that the anions are larger than the cations. So let's take a look. This is an isoelectronic set that I gave you. I'm going to switch colors because we're using a lot of red up here. So just so we're clear, let's use blue. All right, and when I take a look at this here, I'm going to say, all right, well, the ones that I have are calcium, potassium. I retreat back and then I look at chlorine and I look at sulfur. Those are the sets that I have here. Okay, so they're all isoelectronic. These guys right here are cations. Remember that cations get smaller because we're tossing electrons out while keeping the same number of protons. And so that is able to pull in the remaining electrons more effectively. Whereas when I deal with calcium and sulfur as anions, I'm going to start seeing larger and larger, and particularly sulfur because it has 2 extra electrons and did not increase its protons. The answer here is B. Sulfur is going to be the largest ion of that isoelectronic bunch. So hopefully you guys found all of this useful. I'm going to clear the screen here and we're going to just go over a very brief recap so that you understand the takeaways from this lesson. Alright, so here's a brief recap in terms of everything we've talked about over the past hour lecture. So first of all, Z effective, or effective nuclear charge, states how tightly a nucleus can pull the electrons, the valence electrons, in towards itself. This is going to increase from left to right, going across the periodic table, and it's going to increase from top to bottom, meaning as we get closer to the bottom, we're going to see an increase in Z effective. This also helps to explain the other trends quite well, so that's why we spent some time with it first. Atomic radius, the distance from the nucleus to the outermost electrons, or the valence electrons. That's the definition of an atomic radius. You're going to decrease with this trend from left to right. It's kind of the opposite of the other trends. So that means we get smaller, we decrease as we go to the right. It's going to increase going from top to bottom, and that's because the shells are expanding as we get out towards the bottom. Remember that cations, so we're talking about ions now, cations are going to form smaller counterparts to their normal elements, and anions are going to form larger. That has to do with keeping the number of protons the same while removing for cations, which means the protons have a greater effect. We're removing electrons. And in an anion, we are not increasing the protons, but we are increasing the number of electrons, so the protons lose some of their pull. For ionization energy, we're talking about the amount of energy required to remove an electron from the valence shell. It's going to increase going from left to right due to Z effective. It's going to decrease going top to bottom. That's because the shells are putting those valence electrons further from the nucleus, so they're easy to remove. Subsequent ionization energy jumps will always be higher. So in other words, it's always easiest to remove the first electron. It becomes much more difficult for all subsequent electrons as you continue forward. There were two major exceptions to this. The first was when we jumped from an S to a P shell, and that's because the S shell is closer to the nucleus, and therefore those electrons are more tightly held. And then when I say P3 to P4, okay, I'm not talking about the 3p shell and the 4p shell. I'm talking about when you have any p shell with 3 electrons filled, and then any p shell with 4 electrons filled. That jump, because you start pairing those electrons, there's slight repulsion, and it's easier to remove the repulsed electron. So continuing on here, we have electronegativity, and electronegativity is going to increase as we go from left to right. It is going to decrease going top to bottom. And remember, the differences when we're looking at electronegativity are going to allow us to classify our bond as either non-polar covalent if it's between 0 and 0.4, polar covalent if it's between 0.5 and 1.9, and anything above 2.0 is going to start treading into the ionic territory. All right, and then finally, let's move this down just a bit. Okay, electron affinity. When we're dealing with electron affinity, it's going to increase going from left to right. It's going to decrease going from top to bottom. And keep in mind that electron affinity is talking about the energy released when picking up an electron. So if you see these on charts when we're talking about electron affinity, you might see a high negative value. That means a lot of energy was released upon picking up an electron, so that compound or that element would have very high electron affinity. So hopefully this sums it up pretty well. We will see everybody for the next lecture, and until then, make sure you get lots of practice. Thanks a lot, guys.